Dear friends, welcome to Bond with RK Chemistry YouTube channel. In this video, I am going to explain the previous year questions appeared in HCU PG Entrance Examination from the lesson Chemical Equilibrium. In part 1, we have the previous year's questions from 2014 to 2019. Let's take the number of questions appeared in each year. On an average, we have 3 to 4 questions from chemical equilibrium in HCU PG Entrance Examination. Let's take the first question. The solubility of barium sulfate at 25 degrees centigrade is 0.0023 mg per ml. The solubility product Ksp of BaSO4 is close to. Here, barium sulfate dissociates into Ba2 plus and SO4 2 minus. If the solubility of BaSO4 is S, then the concentration of Ba2 plus is S and the concentration of SO4 2 minus is also S. Then Ksp is equal to concentration of Ba2 plus and concentration of SO4 2 minus. It's a product of concentration of Ba2 plus and SO4 2 minus. So S into S, Ksp is equal to S square. Here solubility is given, but the solubility is in terms of mg per ml. In the calculation of Ksp, we have to convert it into mole per liter. So solubility is given in terms of 0.023 mg per ml. When you convert into gram per liter, 0.023, it will be gram per liter. So when you divide with molecular weight, you will get to mole per liter. So molecular weight of BaSO4 is given 233. So it will be 0.0023 divided by 233 mole per liter. So when you simplify this one, okay, this one solubility S is equal to, it can be written as 230 into 10 to the power of minus 5 divided by 233. So finally we will get around 10 to the power of minus 5. So here S is equal to 10 to the power of minus 5. So Ksp is equal to 10 to the power of minus 5 whole square. So this one is equal to 10 to the power of minus 10. So the answer is B. pKa value of hydrofluoric acid is 3.2. The approximate degree of dissociation of 0.35 molarity solution of hydrofluoric acid is. Okay, hydrofluoric acid, it's a weak acid, weak electrolyte, weak acid. So this one is dissociates into H plus and F minus. Let's take the degree of dissociation of hydrofluoric acid as alpha. You have to find out the alpha value. Here pK is given and also concentration of HF is given. We know the relation between alpha, Ka and Ce. Alpha is equal to root over Ka by C for weak electrolytes. Here pK is given. pK is equal to 3.2. We know the pK minus log Ka base 10 is equal to 3.2. So Ka is equal to 10 to the power of minus 3.2. The value of 10 to the power of minus 3.2 is 6.31 into 10 to the power of minus 4. This is the Ka value. and concentration is given. What is the concentration? Concentration of HF is 0.35. So C is equal to 0.35 molarity. So when you substitute these values, alpha is equal to root over Ka 6.31 into 10 to the power of minus 4 divided by 0.35. So when you simplify, you will get around 4.2 into 10 to the power of minus 2. This is a fraction. When you convert fraction into percentage of degree of dissociation is equal to 4.2 into 10 to the power of minus 2. You have to multiply with 100. So this one is equal to 4.2 percentage. So the correct option is C. The equilibrium constant for A2 dissociates into 2A is 2.0 at 30 degrees centigrade. The mole fraction of A at equilibrium at the same temperature is. Okay, equilibrium between A2 and 2A at initial concentration, that is, take initial number of moles of A2 as 1 and this one will be 0. Let's take change. I means initial, C means change. Let's take X moles of A2 are consumed, then it will be minus X since X moles of A2 are consumed, and there is a formation of 2X moles of A. When 1 mole of A2 is consumed, 2 moles of A will be formed. When X moles of A2 are consumed, 2X moles of A will be formed. So it will be 2X plus 2X. So what is the concentration at equilibrium? It will be 1 minus X moles and this one will be 2X moles. Here equilibrium constant is given. At equilibrium, what is the equilibrium constant? K is equal to concentration of A square by concentration of A2 at equilibrium. At equilibrium, what is the concentration? 2X whole square divided by 1 minus X. Okay, this one is given. 2X whole square by 1 minus X is equal to, this one is equal to 2. So that implies 4x square is equal to 2 minus 2x. That implies 2x square plus x minus 1 is equal to 0. So when you solve this equation, you will get x is equal to 1 by 2. When you substitute x is equal to 1 by 2, when you substitute 1 by 2 in place of x, you will get 0. This equation will become 0. So x is equal to 1 by 2. So at equilibrium, what is the concentration of A2? It will be 1 minus 1 by 2. It will be 1 by 2. And this one is 2 into 1 by 2. It will be 1. So the mole fraction of A at equilibrium at the same temperature is. What is the mole fraction? Mole fraction of A is equal to number of moles of A by number of moles of A plus number of moles of A2. Okay, number of moles of A 1 divided by 1 plus 1 by 2. It will be 1 by 3 by 2. It will be 2 by 3. So the mole fraction will be 0.67, nearly 0.67. For the gas phase reaction, H2O plus CH4 gives rise to CO plus 3H2. If Kc is equal to 3.8 into 10 to the power of minus 3 molar square at 1000 Kelvin, the Kp is, what is the Kp value? Here all are in gaseous phase. So this one is gas and this one is gas and this one is gas and this one also gas. Then delta Ng delta Ng. It is the sum of gaseous molecules on product side minus sum of gaseous molecules on reactant side. This is Ng product minus Ng reactant. On product side we have 4 gaseous molecules, 4 minus. On reactant side we have 2 gaseous molecules, 4 minus 2, it will be 2. We know the relation between Kp and Kc. Kp is equal to Kc RT power of delta Ng. So here Kc is given. Kc is 3.8 into 10 to the power of minus 3. RT value, it should be in liter atmosphere. So 0.0821 liter atmosphere mole inverse Kelvin inverse, and the temperature is given, it's 1000. Delta Ng is 2, so it will be 3.8 into 10 to the power of minus 3 into, it will be 82.1 whole square. So finally we will get Kp is equal to 26. After simplification you will get Kb is equal to 26. A 20 ml sample of 0.30 molarity HCl is titrated with 0.15 molarity NaOH. What is the pH of the solution after 40.3 ml of NaOH is added to the acid? We have to find out the pH of the solution. For this we have to find out concentration of H plus or concentration of OH minus. Here there is a neutralization between acid HCl and the base sodium hydroxide. For this we have to calculate first NaVa. This is the normality of acid and the volume of acid, and also NbVb, normality of base and volume of base. Here acid volume is 20 and concentration is 0.30 molarity or normality. So 0.30 into 20, this one is 0.15 into, this is the volume of NaOH, 40.3. This one is equal to 6, this one is equal to, you will get 6.045. Here NbVb is greater than NaVa. When NbVb is greater than NaVa, the resultant solution will be in basic. So you have to find out the concentration of OH minus. Here the concentration of OH minus is equal to NbVb minus NaVa by Va plus Vb. So this is the formula of concentration of OH minus when NbVb is greater than NaVa. When NaVa is greater than NbVb, then you will get concentration of H plus is equal to NaVa minus NbVb by Va plus Vb. So here concentration of OH minus is equal to NbVb 6.045 minus 6.000 divided by Va plus Vb. Va is 20 and Vb is 40.3. You will get 60.3. So when you simplify, you will get OH minus concentration is equal to, it will be 0.045 divided by 60.3. You will get around 7.46 into 10 to the power of minus 4 molarity. Then concentration, then POH is equal to minus log concentration of OH minus, so it will be equal to minus log 7.46 into 10 to the power of minus 4. So you will get after simplification you will get POH is equal to around 3.127. Then pH is equal to 14 minus 3.127. it will be equal to 10.87, nearly 10.87. So the correct option is 10.87. The degree of dissociation of an aqueous solution of a weak acid at pH is equal to 4.74 is. Okay, pK is given. pK is equal to 4.74. Let us take weak acid HA. This one dissociates into H plus and A minus. Let's take degree of dissociation as alpha. Initial concentration, let's take C, and this one is 0 and 0. If the degree of dissociation is alpha, then change in concentration, here C means change, this one is initial. The change in concentration will be minus C into degree of dissociation, C alpha. This one is plus C alpha, this one is plus C alpha. So Ka is equal to dissociation constant, Ka is equal to concentration of H plus, that is C alpha, into concentration of A minus C alpha divided by concentration of HA at equilibrium. Okay, at equilibrium you have C minus C alpha, this one is C alpha, this one is C alpha. So C minus C alpha, it can be written as C into 1 minus alpha. So here there is a cancellation of C terms. So finally you will get C alpha square by 1 minus alpha. This is the Ka. From this one, what is the concentration of H plus? H plus concentration is equal to C alpha. When you take the ratio between Ka and concentration of H plus, okay, this one is equal to C alpha square 1 minus alpha divided by C alpha. So you will get, there is a cancellation of C alpha terms, C and 1 alpha term. So you will get alpha by 1 minus alpha. Here pK is 4.74. From this, Ka is equal to 10 to the power of minus 4.74. Okay, Ka is equal to 10 to the power of minus pK. And concentration of H plus is equal to, it's a 10 to the power of minus pH, 10 to the power of minus 4.74. Okay, both are same. Ka is equal to H plus concentration. So here Ka 10 to the power of minus 4.74. This one also minus 4.74. So there is a cancellation. So alpha 1 minus alpha. Finally, alpha by 1 minus alpha is equal to 1. So that implies alpha is equal to 1 minus alpha. So 2 alpha is equal to 1. Alpha is equal to 1 by 2. So the degree of dissociation alpha is equal to 1 by 2 means 0.50. The equilibrium constant of a gas phase reaction is 2.0 at 400 Kelvin and 3.0 at 500 Kelvin. The standard enthalpy of this reaction is close to. Okay, here there is a relation between equilibrium constant and temperature. This one is given by want of equation. According to want of equation, log K2 by K1 is equal to delta H naught by 2.303 or 1 by T1 minus 1 by T2. So this is the relation between K2, K1, T1, T2 and delta H naught. Okay, from this you have to calculate delta H naught value. Log K2 by K1, K2 and K1 is given. This is K1 and T1, K2 and T2. So log K2 by K1, it will be 3 by 2. 3 by 2 is equal to delta H naught 2.303. Here R should be in terms of calories. So 1.98 into 1 by T1 minus 1 by T2. So 1 by 400 minus 1 by 500. So that implies delta H naught is equal to log 3 by 2 into 2.303 into 1.98 into this one 400 into 500 divided by 100. After simplification, you will get delta H naught is equal to 1610 calorie mole inverse. So when you convert into kilocalorie, it will be 1.610 kilocalorie mole inverse. So the correct option is B. The following solutions are mixed together in a beaker. Predict from which solution CaF2 will be precipitate. The condition for the formation of precipitate is ionic product KIP should be greater than KSP. The ionic product should be greater than solubility product. So you have to calculate ionic product. In case of A, 100 ml 2.0 10 to the power of minus 4 molarity Ca2 plus ions plus 100 ml 2.0 10 to the power of minus 4 molarity F minus ion. Here the total concentration of Ca2 plus will be, if you take A, it will be 100 into 2 into 10 to the power of minus 4 divided by the total volume. You have to divide with the total volume. It will be 200. This is the concentration of F minus. Sorry, Ca2 plus. This is the concentration of Ca2 plus. What is the concentration of F minus? F minus will be 100 into 2 into 10 to the power of minus 4 divided by 100 plus 100, it will be 200. So cancellation of 200. You will get concentration of Ca2 plus is 10 to the power of minus 4. This one also 10 to the power of minus 4. So ionic product is equal to concentration of Ca2 plus 10 to the power of minus 4 into concentration of F minus square. What is ionic product? For CaF2, ionic product is equal to concentration of Ca2 plus and F minus square. So it will be 10 to the power of minus 4 square. So it will be 10 to the power of minus 12. 10 to the power of minus 12 is, this one is less than KSP. So in this case, there is no formation of precipitate. So let's take the B option. In this case also Ca2 plus concentrations will be 100 into 2 into 10 to the power of minus 5 by 200. This is concentration of Ca2 plus. What is the concentration of F minus? F minus will be 100 into 2 by 2 into 10 to the power of minus 5 by 200. So you will get 10 to the power of minus 5. This one also 10 to the power of minus 5. So ionic product will be 10 to the power of minus 5 into 10 to the power of minus 5 square. So it will be 10 to the power of minus 15. This one is less than KSP. In this case also there is no precipitation. Suppose if you take this one, the concentration of Ca2 plus will be 100 into 2 into 10 to the power of minus 2. Let's take C. 100 into 2 into 10 to the power of minus 2 divided by 200. This is the concentration of Ca2 plus. And F minus is 100 into 6 into 10 to the power of minus 3 by 200. Here 200 cancel. So 10 to the power of minus 2 is concentration of Ca2 plus, and F minus will be 3 into 10 to the power of minus 3. So what is the ionic product? Ionic product is equal to 10 to the power of minus 2 into 3 into 10 to the power of minus 3 whole square. It will be 9 into 10 to the power of minus 8. This one is greater than 4 into 10 to the power of minus 11. So in this case there is a precipitation. Similarly, if we calculate ionic product for D, this one is smaller than 4 into 10 to the power of minus 11. So here there is no formation of precipitate. So correct option is a sample of 4.6 gram N2O4 taken in a 1 liter flask at 27 degrees centigrade dissociates partially to NO2 gas. If the equilibrium total pressure is 1.4 atmosphere, calculate the fraction of N2O4 dissociated, assuming perfect gas behavior for all. Here N2O4 dissociates into 2NO2. N2O4 is gas and also NO2 is also gas. Here number of moles of N2O4 we have to calculate. N2O4 is equal to 4.6 weight by gram molecular weight, 4.6 by 92. This one is equal to 5 into 10 to the power of minus 2. So initially the number of moles of N2O4 is 5 into 10 to the power of minus 2. This one is 0. At equilibrium, if the degree of dissociation is alpha, then the concentration will be 5 into 10 to the power of minus 2, 1 minus alpha. This one is 2 into 5 into 10 to the power of minus 2 alpha. Okay, let's take this one is C. It will be C into 1 minus alpha. This one is 2C alpha. This one is concentration. Let us take. It will be 2C alpha. Okay, this is a concentration of N2O4 and NO2 at equilibrium. And also at equilibrium, the total pressure is given. At equilibrium, what is the total pressure? 1.4 atmosphere. From this, we can calculate number of moles. N is equal to PV by RT. Okay, what is the pressure? 1.4, volume 1 liter, and R 0.0821 liter atmosphere, mole inverse, Kelvin inverse, and temperature is 27 degrees centigrade. So it will be 300 Kelvin. You have to add 273 to 27. You will get 300. So when you simplify, you will get N is equal to 5.684 into 10 to the power of minus 2. Okay, this is the total number of gaseous molecules at equilibrium. From this, the total number of gaseous molecules will be 5 into 10 to the power of minus 2, 1 minus alpha, plus it will be 10 into 10 to the power of minus 2 alpha is equal to, this is the total number of moles, 5.684 into 10 to the power of minus 2. Okay, when you solve this equation, you will get to finally alpha is equal to 0.14. Ionization constant Kw of water at 37 degrees centigrade is 2.42 into 10 to the power of minus 14 mole square later power minus 2. The pH of neutral water at this temperature is, Kw is given, Kw is concentration of H plus and concentration of OH minus, is equal to 2.42 into 10 to the power of minus 14. At neutral condition, concentration of H plus is equal to OH minus. So concentration of H plus is equal to OH minus at neutral. So Kw is equal to concentration of H plus. In place of OH minus, you can write concentration of H plus. So H plus square is equal to 2.42 into 10 to the power of minus 40. So the concentration of H plus is equal to root over Kw, that is 2.42 into 10 to the power of minus 14. Okay, the root term 2.42 into 10 to the power of minus 14 root will become 1.5556 into 10 to the power of minus 7 molarity. Then pH is equal to minus log concentration of H plus, this one is equal to minus log 1.5556 into 10 to the power of minus 7. So when you simplify, you will get 7 minus log 1.5556. Okay, after that you will get around 6.8. So this is the correct option. Acetic acid is a weak acid in aqueous solution. In sulfuric acid, it behaves as, it's a weak acid. Okay, let's take CH3 COOH. In aqueous medium, it's a acid, but in presence of strong acids such as H2SO4, CH3COOH accepts proton and it will become OH plus and OH plus HSO4 minus. So this one donates H plus, so it's acid. It accepts H plus, acceptor, H plus acceptor, so it's a base. In presence of strong acid, weak acid will behave as base. So weak acid, acetic acid will be base. What is the concentration of H3O plus in your solution at 25 degrees centigrade that has pOH is equal to 5.64? At 25 degrees centigrade, pKW is equal to pH plus pOH is equal to 14. pKW is 14. So pH is equal to 14 minus pOH is equal to 14 minus, what is the pH value? 5.64. So pH is equal to 14 minus 5.64 is equal to 8.36. So concentration of H plus is equal to 10 to the power of minus 8.36. So this one is equal to 4.37 into 10 to the power of minus 9. So D is the correct. In common ion effect, if a salt Mx is added to an aqueous solution containing the solute My, M is common to both the salts, presence of the dissolved Mn plus ions. In common ion effect, the common ion suppresses the solubility or dissolution of salt Mx. So what is the correct option? Suppresses the dissolution of Mx compared with that in pure water. In pure water, this is a dissolution, this is a dissociation. But this is water, in pure water. But in presence of Mn plus, when you introduce Mn plus, so on right side you are increasing concentration of N plus, so the equilibrium will be shifted towards Mx. So it suppresses the dissolution of Mx. Which of the following can be added to maintain the pH of an aqueous solution when CO2 is dissolved in it? We know that buffer solutions maintains the pH, constant pH. The buffer solution is a combination of weak acid and salt of weak acid, or it's a combination or mixture of weak base and salts of weak base. When you dissolve CO2 in water, there is a formation of weak acid, that is carbonic acid H2CO3. So when you add salt of this weak acid, suppose if you take NaHCO3, when you add NaHCO3 to H2CO3, it acts as a buffer solution and maintain the pH. So which one will maintain the pH of an aqueous solution when CO2 is dissolved in it? Sodium bicarbonate. Given the following reaction at equilibrium at temperature T, N2 plus 3H2 and 2NH3 Here I am taking all our gases. Let us take gas, this one also gas. Then what is the relation between Kp and Kc? For this we have to calculate delta Ng. Delta Ng of products minus Ng of reactants. Gaseous molecules on product side minus gaseous molecules on reactant side. So here delta Ng is equal to product side we have 2 gaseous molecules, on reactant side we have 4. So it will be minus 2. We know the relation between Kp and Kc. Kp is equal to Kc RT power delta Ng. So it will be equal to Kc RT power delta Ng. It will be minus 2. That implies Kc is equal to Kp into RT power whole square. So what is the relation? Kc is equal to Kp into RT whole square. Consider the following reaction scheme involving an equilibrium followed by a rate determining step. The apparent rate constant for the formation of the product is given by the formation of the product. Here, rate of formation of product, rate of formation of product is equal to rate constant K into concentration of Z. Okay, from equilibrium, concentration of Z can be written as, we know that capital K equilibrium constant is equal to concentration of Z by concentration of A into concentration of B. So Z, concentration Z is equal to K, capital K into A into B. So in place of Z we can substitute this one. So R is equal to small k, capital K and concentration of A, concentration of B. So here the apparent rate constant, it's a product of rate constant small k and equilibrium constant. So small k into capital K. 50 ml of a 0.1 molar acetic acid was taken, it's a weak acid, in a 100 ml conical flask, and exactly 2 drops of dilute solution of phenolphthalein indicator color transition range 8.8 to 10.0 were added to it. The solution was titrated by incremental addition of 0.10 molarity NaOH solution from a burette. Calculate the pH at which the mixture in the conical flask is neutralized. Okay, it's a neutralization between weak acid and strong base. So if you take neutralization point of weak acid and strong base, it's always greater than 7. So this one is wrong, this one is wrong. So minus 7, this one also wrong. This one is greater than 7, 8.73 is greater than 7. So the neutralization point will be around 8.73. pH of the solution prepared by mixing 50 ml of 0.3 molarity NaOH and 50 ml of 0.1 molarity HCl would be. So for this we have to calculate NaVa and NbVb. Here molarity of HCl is 0.1 normality or molarity into 50. This one is 0.3 into 50. Here molarity and normality both are same. This one is 5, this one is 50. Since NbVb is greater than NaVa, so the resultant solution will be basic. So we have to calculate concentration of OH minus. OH minus concentration is equal to NbVb minus NaVa by Va plus Vb. NbVb is 50 minus 5 by total volume is 100. So 10 by 100. This one is equal to 10 to the power of minus 1. So POH is equal to minus log OH minus concentration is equal to 1. So pH is equal to 14 minus pOH is equal to 14 minus 1 is equal to 13. So what is the concentration of the resultant solution? Is 13. Thank you very much.